Okay, so thanks for the introduction. And yeah, my name is Jeronimo. I'm a professor in Dresden, and we've been working on high-level compilation things. And I think the presentation before by Gerardo is a very nice introduction to what I will be talking about. Okay, so we've been working on like emerging architectures and heterogeneous systems, like things like FPGAs with access to high bandwidth memory. Or also for the AI accelerators, here in this case, a picture from AMD with their AI engines. And for the purpose of today, near memory computing, like here the Samsung architecture or the ABUMPIMP architecture. And I'm also going to talk a little bit about in-memory computing with different technologies. So this is kind of the heterogeneous landscape in which we try to work on compilers and programming abstractions. So we need new paradigms, and we saw a little bit of that in the talk before. And just to give a motivation why we need these abstractions, I usually give this example here, where you have a very simple mathematical expression. This is a tensor interpolation that appears in HPC and in many other application domains. And if you go and program that in C, in a very naive way, you would write this piece of code. So this is a direct implementation of the multiplications, right? You see all those for loops, and here somewhere you'll find that expression like almost one-to-one, right? The three matrices multiplied by the four-dimensional tensor U. If you do that today and you pass it to a compiler, the performance that you get is like 100 times slower than the hand-optimized version that you see here, which has some pragmas for SIMD, some pragmas for OpenMP, and this is on Intel CPUs, not even talking about more complex architectures. So that's kind of what motivates this needs for new abstractions, needs for new programming models, and so on. Because if we cannot make it work on a CPU architecture, it's hard to imagine that we can make it work on the accelerators that I was talking about before, like on the AI engines or on a system running on FPGA with access to high bandwidth memory and near and in-memory computing. That's kind of what motivates the title of the talk today. And so we have worked on these different targets. Today I'm going to be focusing more on this area here, near memory and in-memory computing, as you'll see. Okay, so yeah, we did this new abstraction so that we can actually target this more fancy, exotic, emerging architectures. So let me talk a little bit about abstractions. So how do we define them and how do we use them? So I'll use the example that I showed you before. So actually the code that I showed you before, the one that was handwritten, was actually not handwritten. It was written by our compiler, and it matched the handwritten code that was available to us. It was actually Fortran code that people use in HPC simulations for this sort of application. What you see here in this figure is kind of a computational fluid dynamics application with very complex vortexes for which they use something called spectral element methods. So that was kind of the motivation, the starting point for this language that we defined some years ago, 5-6 years ago. So you have different incarnations of this language. The first one is an embedded in Fortran. The second one you see in the bottom is just using template metaprogramming in C++. And with the compiler that we created back then, we actually managed to get very good performance. Here, the x-axis just shows you the polynomial degree. So to the right, the problem is more complex. And on the y-axis, you see the gigaflops, so higher is better. Here in these two plots, the magenta ones, is kind of what you would get if you use MKL libraries. This is the default one, and this one is optimized for the sizes that we would get at runtime while executing this code. And in blue was the handwritten code in Fortran. Green and red is the one that we generated with the compiler. And so we were very happy with these results because we were able to match and actually improve over hand-optimized code, just starting from a very high-level expression like this one or this one over here, right? So yeah, that was quite good. And this is nothing that is just because I'm presenting here and this is our framework. There's a lot of so-called DSLs, domain-specific languages, and compilers that show that if you architect those abstractions intelligently, the compiler can actually outperform manual code most of the times for these specific domains. And here's a bunch of examples, spiral talk. I mentioned lift in the talk before. So lift show that for map, zip, window, those kind of functional patterns. And there's a lot of other DSLs that have shown that given the complexity of architectures today, if the compiler has a high-level view of the semantics of what you want to execute, it's not that hard to outperform standard compilers, but also manually optimized code. So I said that what do we do? How do we encode these abstractions? So before 2019, we were writing our own compilers. Like the one that you saw before was written just with standard old-school compiler tools. In the last years, we have been working very actively on MLIR. So MLIR is a compiler framework that was open source by Google, with which you can actually find your own abstractions. So here is a diagram of how that would look like. You have some DSLs, and inside MLIR, the MLIR framework, you can define some languages. These are intermediate languages, like for instance, lineage is an intermediate language that understands the primitives of linear algebra. There are some intermediate languages for stencils, for affine loops, and so on. So you could then, if this is the language that you want to define, you can then define high-level transformations on the basis of linear algebra operations. Okay, so that's kind of the idea of MLIR, and that's what we've been working on for the past years. So in this framework, you can then do this progressive lowering, where you go from a high-level DSL abstraction, for instance, a dialect that expresses TensorFlow operations in machine learning, or a dialect that expresses those tensor operations in computational fluid dynamics. And then you do this progressive lowering where you go down these levels of the stack. And tensor that you saw, the tensor language that you saw before, is now also a dialect in MLIR. It lowers to this, what we call TILE, this tensor intermediate language, tensor expression intermediate language, and from there we can go to lineage, and then we can do some other transformations that allows us to do some optimization, as you will see in the coming slides. Okay, so now let's focus now on near memory and in-memory computing. So I think you know what is the motivation for this sort of architectures. We want to kind of remove the von Neumann bottleneck of moving things into the data path of the CPU, and there's a lot of such architectures for near and in-memory. So we call near memory computing when you have some processors close to the memory. For instance, if it is close to DRAM, like in the case of ABUMPIMP, that's those TPUs that sit in the DIMMs. We say it in-memory computing when you actually leverage the physics of the cells that store data to compute, right? And there are multiple examples of those things. And here's an overview paper with commercial and academic examples of these architectures. So there's a lot of different proposals, but there are commonalities, right? So most of these things are hierarchical because the way we architect hardware, right? So you have DIMMs, you have banks, you have arrays, subarrays, mats, and so on and so forth. And some of them will be architected so that you can support some common high-level operations. So here I'm using this slide from Michael Niemeyer from Notre Dame, where he shows this kind of very crazy landscape where you have a lot of devices here on the bottom. Like these are really devices, nanoelectronic devices, some of them PCM, some of them ReRAM, and so on. And what kind of primitives or what kind of architecture templates you can build with them, like for instance, crossbars, so that you can accelerate matrix-matrix multiplications or matrix-vector multiplications and so on and so forth. Or here where you have content addressable memory, so you can accelerate distance-based computations. So there's a lot of as I say, a colorful landscape of options that you can use. And that's what we've been studying in the past 5 years or so. And so we came up with kind of an abstraction of those weird, like hardware and exotic architectures into what could be understood as maybe as a generic instruction set architecture of things that you can execute near memory or in memory. And we call that Cinnamon. This is just compute in and near memory. That's a short name for that, and we pronounce that Cinnamon. And this is an example of that table of operations, what kind of types they have. And if you go into the paper, you will see with what kind of architecture support this operation or that operation. Okay? So yeah, so we built this compiler using MLIR, as I mentioned before. And in that way, we can target this near memory computing systems like ABUMPIMP, but also this in-memory computing systems that are more kind of a research, research prototype status. So what we do with this is that we can do some pattern recognition so that we can identify some of the patterns that people write, for instance, in Python, like the patterns that you would describe or the code patterns that you would use to compute distances, or the compute patterns that you would use to implement some tensor operations as you saw before. Yeah, so the flow looks more or less like this. So there are different papers that talk about a little bit about our compiler. So today it would look something like this. You can get into the compiler with some of these languages, but anything that maps down to maybe the Torch dialect or the Lineage dialect or the Tosa dialect can be then piped into our Cinnamon abstraction. So this will be the language that understands things that could run near memory or in memory. And then you have dialects that then specializes for near memory or memory, and then further specializes for the type of system that you have. For instance, if you have a crossbar, or if you have ABUMPIMP, so there's a dialect that understands the primitives of ABUMPIMP, and the compiler will then translate those things automatically. And here, similar to what you saw in the presentation before, the idea is that the programmer does not have to code using the ABUMPIMP API, but you can code something very high level using PyTorch or using some DSL for HPC, because this is not just for ML, but also for other type of application domains. And the compiler will automatically insert all those primitives, the allocation of memory, placing data into memory, allocation of communication primitives, and so on. So yeah, so as I said, there are some commonalities here. You see the ABUMPIMP diagram, also the diagram from the Samsung system. So you have many PIM units. These PIM units will have, some of them will have some fixed functions, like in the case of Samsung, or some general purpose processor units, like in the case of ABUMPIMP. You have multiple address spaces. Some of the computation can be synchronous or asynchronous. All of these things have to be modeled within the compiler. So the abstract programming model is similar to GPU. You have some kind of scatter, execute, and gather. And this would be the code that you would have to write in the case of ABUMPIMP for matmult. Maybe this is a little bit outdated, but that's the one that we use to motivate these slides. And so if you show this to a high-level programmer, this looks very low level, right? So there's a lot of memory, explicit memory addresses encoded into this program. So what we want is people to be able to execute, to write these things, matrix multiplication, in a higher level language. It is an example of such a language where you just do what you expect, right? So you have some two matrices A and B, and you compute the product and you store it into C. This is a very high level abstraction, similar to what can be fed into our compiler. And so there's a couple of lowering processes. So first, say that the pattern matching will identify that this is just a gem, right? So that's what you say, you see here. That's one of the basic primitives in the Cinnamon abstraction, because many, as you saw before, many of the near memory or in-memory computing architectures are optimized to provide fast gems primitives. This is then, for instance, lower so that it fits hardware. In this case, I'm showing an example of tiling. So tiling is a very common compiler optimization. In this case, these tilings, you see different versions of the tiling. So tiling the output array into squares or into these linear rectangles. And in the case of ABUMPIMP, for instance, kind of in the compiler, while developing the compiler, we found out that this linear tiling thing was the one that worked the best, right? Because of the sizes of the working RAM and so on and so forth. So that's a tiling decision that the compiler will take automatically while lowering the code. Then it moves on, right? So you see this tiling. So inside of the tiling, you still have the Cinnamon operation that corresponds to general matrix multiplication. This can then further lower to Cinnamon, to CNM. So this is the dialect that now closely matches things that you can execute near memory, not necessarily ABUMPIMP, but something that executes near memory. And then you see a lot of more low-level primitives here. Here you see the scatter, kind of launch a kernel. Here you see the reduce, for which we use the lineage reduce. So here you see the benefits of working with MLIR is that we can actually we don't have to lower everything at the same time, but multiple abstractions live at the same time in a given implementation or in a given lowering step within the compiler. And you see the gather here below. So here then at the end we generate code for the final stage. We generate code for the host codes. It's still in the MLIR world. So we have an ABMEM part that goes onto the host, and an ABMEM part that goes into the device, where you see the copying from MRAM to VRAM to working RAM, and so on and so forth. Okay, so how does this work? This is similar to what Gerardo was presenting before. Here we're using, I think this is the polybench benchmark fit. This is the polybenchmark fit. Here we're just studying what do we achieve if we increase the amount of DIMMs. So here you have 4 DIMMs with 8 DIMMs and 16 DIMMs. So 16 DIMMs, we're using 2048 DPUs. And so it is expected that the performance improves. So this is kind of showing that the compiler is able to, if we allow the code to use more DIMMs, the compiler will act accordingly, and we are able to exploit more parallelism from the same specification in a very high-level language, right? So all these benchmarks are written in a very high-level language, nothing particular to the ABMEM system. The other thing that you see, like in the bluish, in the greenish, and the lightest color, is that with optimization you gain something, right? If we allow some optimization with the compiler, you can achieve 50% speed up with the optimization that we implemented in the compiler. We also, to show that this is not just for this polybench kind of benchmarks, we also looked into the PRIM benchmark that was mentioned also before, where we have, there's some manually optimized code available, so we could compare to that. And here you see that compared to the manual designs, Cinnamon can execute, so the manual designs already executed 2 to 5 times faster than CPU. And compared to those manual designs, Cinnamon achieved 1.5 to 2x improvement, which is actually pretty good, right? So we are, as I said before, we are able to beat hand-coded implementations of these benchmarks, and we're using 10 to 40 times less lines of code, similar to what Gerardo was mentioning before. So this is another metric that shows that you're using, so the code complexity is 40 times smaller, and still you get better performance because of our compiler. Okay, so that's what I had to show about ABMEM. I wanted to, just since this is a general talk a little bit about other stuff that we've been doing. I mentioned in-memory computing, and an example of in-memory computing that is pretty common is that of using crossbars, where inside the memory you have some devices. It could be PCM, it could be some ReRAM cells, and you can use those ReRAM cells or those PCM cells to also compute in the analog domain matrix vector multiplication. So basically, the activations will be the input to the memory, and once you put the activations as input to the memory, what you read as output corresponds to the dot product between the activations and this column, the dot product between these activations and this column. And so in the end, this things here is the result of a matrix vector multiplication in constant time. So this is why this kind of accelerators have been studied quite a lot in the past years, because they can accelerate matrix vector computations and do that in constant time, at least for the size of the crossbar array. So yeah, so we did this. So Cinnamon also is able to target simulators that can can model those sort of architectures. And here you see, in terms of execution time, as expected, you will see orders of magnitude improvement, like 2 orders of magnitude improvement in execution time for the benchmarks that are heavy on matrix multiplication, of course. And the same happens in terms of energy efficiency. So you see 2 orders of magnitude improvement in performance, and also kind of 2 orders of magnitude improvement in energy consumption. So it's kind of, if the benchmark is heavy on matrix multiplications, so you would expect 3 to 4 orders of magnitude improvement in terms of energy efficiency, which is pretty good, right? And that's why these things are so popular. But of course, there's a lot of challenges with these architectures that I'm happy to talk about in a break or something. Okay, so I mentioned CAMs before. So there's also this idea of using content addressable memories to accelerate some parts of some artificial intelligence algorithms, for instance, some few-shot learning algorithms that are out there, or hyperdimensional computing. And the idea of CAMs is that you put a pattern, and the memory will give you the index or the closest index that matches that pattern. So it's a very good accelerator to do kind of k nearest neighbor searches. let me skip a little bit about that. So here, similar flow. You can start with PyTorch. You can also pass a description of the architecture to the system. So you start with a very high-level algorithm like this one here. That's PyTorch code, where you have some norm. You just want to get the top K, and all of this can be then lowered into the seam abstraction. Here you see this is the seam abstraction, and then this can be then moved depending on what kind of CAM you have. If it is an MCAM or a ternary CAM, you get some of this implementation. And if you have support for selective search, then this is also kind of automatically understood by the compiler. And yeah, so this is a thing that we published in ASP+ this year. So we compared against manual designs in GPUs, and you see that in terms of latency and in terms of energy consumption, using CAMs, and depending on the optimization, you're very good off. So how good? Like 14 times faster and 4 orders of magnitude less energy compared to a GPU, which is pretty good, right? That's why this more exotic architectures are quite interesting to look at. The last work that I want to talk about is something that we presented this year at DAC, and this is logic in memory. So we've been also working. So if you remember, I bet you remember the table of instructions that you can execute near or in memory. There's also a lot of logic in memory architectures. For instance, Onur Mutlu has a lot of work done on in DRAM logic operations. And here we're using architecture in a collaboration with the group of Mehdi Tahori. We're using architecture that is able to do logic in memory by specializing or doing logic operations on the columns of a non-volatile memory. And here we were showing that we could, with optimizations, improve the performance. So here you see the latency is 3 times better, but we're also improving the reliability, right? Because we are using, through our optimization, we can use less multi-operand operations, and the multi-operand operations lead to kind of reliability issues in these memories. So it's a kind of a win-win in both cases in our using our toolflow. Okay, and here again, so you see some orders of magnitude improvement in terms of energy delay product with respect to a CPU baseline. But as I said, once you do things in memory, performance, if the benchmark is suitable for that architecture, the performance is off the charts. Okay, so let me close this talk. So we've been working on automatic optimization for heterogeneous in-memory computing. It means near memory, in memory, and also high bandwidth memory, and so on and so forth. I'll talk a little bit about abstractions for domain-specific computations in AI, but also in some HPC domains, because we're in an HPC conference this week. I talked a little bit about how we abstract those primitives from different sort of architectures into our MLIR framework. And I think this is a very good vehicle to implement in this safe and correct by construction optimizing compilers. And that's what we've been working on. There's still a lot of challenges to come up. We're still working on a lot on this modeling of primitives, maybe formalizing the semantics of those primitives to do also formal proofs of correctness. Work on simulators, we'll see some works today on that. And something that I found very interesting in a session that we had date this year is how can we actually go even deeper into this stack of abstractions in architectures and compilers, and do co-design even of the geometry and device parameters. That's something that we've been talking about with colleagues that work with devices. So this is a kind of going from a PyTorch implementation all the way to the geometry of devices. I think that's very exciting. Okay, I'd like to thank the people in my group, especially today Hamid is here, and Hamid would really know what all this is about, so he can take some questions. Hamid is here, there, yeah. So ask him for the details. So he's been leading a lot of the efforts that I talked about today. Yep, thank you very much. I'm open to questions.